Hello, everyone. Greetings to the second day of the Graphene event. My pleasure today is to introduce Rob Anstey. He is CEO and co-founder, I believe, from GDI, which is short for Graphenix Development Incorporated. And today he will tell us about their GDI silicon anodes paired with carbon nanotubes for lithium-ion batteries. Rob, the stage is yours.
Thanks a lot. Really appreciate it. Thanks everybody for your time today. Great presentation so far. Really enjoyed the last one. And we are GDI. We're working on 100% silicon anode, so it's a little bit different than the last presentation you saw where they're adding it as an additive up to 30%. We're going straight to 100%. And we're coming out of stealth and going into commercialization this year. So obviously, everyone attending this conference knows how important it is that batteries get better. They affect every area of our life, whether it's our transport to the phone in our pocket or our laptop or the way we get to work. And they need to be better. And this is the generation of a vast improvement in batteries with all sorts of different chemistries and innovations. So Europe in particular is driving this forward very, very rapidly with announced over a terawatt of battery manufacturing. And the demand is increasing dramatically. Now, this does create an issue. We need a supply chain. We're going to have terawatts of cell manufacturing, but it's critical that we also have a supply chain both in Europe and America that can actually supply these gigafactories with advanced materials. Otherwise, as you've heard in the news just the last several weeks, battery factories may not have the materials necessary to even make batteries. That obviously would be a big issue. So, we believe in silicon. Why? Well, as you can see in other presentations, graphite's kind of hit its limit. Can't do fast charging without lithium plating. It can't go to higher energy without adding silicon. It's tapped out. So how do we get beyond graphite? How do we get beyond carbon materials that have these safety issues, these charging issues, and these energy issues? Well, there are really only three choices that we can think of. One is the different oxides, niobium, tungsten oxides. The issue there is that material is even more expensive than the other materials on this list. So, and it only stores slightly more energy than graphite. So yes, it's got great safety and very fast charging, but it's going to be crazy expensive compared to the graphite that we use today. On this other side of the spectrum is lithium metal. People have been trying to get lithium metal to work since the 90s. It still has interfacial issues. It has a lot of manufacturing issues. At the moment, silicon metal foil cannot be made at massive scale, and it costs anywhere from $250 to $1,000 a square meter. Obviously, that's far, far away from being commercial. That leaves us with silicon. Silicon, depending on how you make it, is already made at very large scale. It can charge incredibly fast, and it stores a lot of energy. So, without realizing it, silicon is already all around us. It's in our glasses, our windshield, it's in skyscrapers, it's in our solar panels, it's in our computers. So it's something that has actually already been very matured in different ways of manufacturing and different supply chains. You can get the raw material from quartz or sand. You can process that raw material into a variety of different feedstocks, and it's already manufactured at huge scales, just not in the way the battery industry is used to acquiring it, which is focused on powder-based. It's actually scaled to massive scale, like, for example, the Shard in London, which was completely coated with vapor deposition. The entire skyscraper. So it turns out things like vapor deposition are actually very scalable and very cost effective. It's just the battery industry isn't aware of that. So we need to increase safety, range, better lifetime, and faster charging. How does GDI help? Well, we have a 100% silicon anode that can be integrated directly into any cell format, directly coated onto copper. This prevents all lithium dendrites. One of the major safety issues and one of the major fast charging barriers is lithium plating. If you have carbon in your anode, you can plate lithium. Any carbon, you can plate lithium on that carbon. That prevents you from going to these 15-minute charging hundreds of times, because that's going to kill the cell. When you try to charge it 15 minutes and you plate lithium or form dendrites on the carbon material. So in order to get rid of dendrites, you have to get rid of the carbon. You have to go to 100% silicon. Silicon's at a 0.5 voltage difference, and it can store almost as much lithium as lithium. So that prevents the formation of lithium plating and dendrites. That also allows you to go to much higher range, because you can store anywhere from 3 to 10 times more lithium than a graphite or a carbon anode. And long cycle life is all